previous lecture, we talked about two different coordinate systems that we use to describe the motion of particle moving under the influence of a force. In this lecture, we start with how to solve the equation of motion when the particle is moving under constraints. So what we are going to talk about is the constrained motion. And I'll explain to you what we mean by that and how do we go about solving this. Suppose there is a particle that is moving under the influence of a force F, then its motion is described by equation of motion that is given as ma equals the applied force, where m is the mass of the particle and a is its acceleration. Written in terms of its coordinate, I can write this as m r double dot equals f, where double dot denotes second derivative with respect to time. Of course, if the particle is free to move, that means it can go anywhere. Then I solve this equation and get r as a function of time given a force. On the other hand, if I restrict its motion, and I'll talk in a minute about what I mean by restricting its motion, the motion can be quite different. For example, I could take a bead moving on a straight wire. And the bead can move only along this wire, and let us say this wire is in x direction. Then no matter what force I apply on this bead, the bead is going to move only along the x direction. Therefore, its motion is restricted. As another example, which is quite well known and also known as Atwood's machine, is two masses moving on a pulley when they are tried by this string. In this case, the masses are no longer free to move. That means if I have this mass m1 and the other mass m2, m1's motion is not determined by this equation alone. That is, its motion is affected. This is not correct. Its motion is affected by the presence of the other mass. Similarly, motion of m2 is also affected by the presence of mass m1. And this constraint comes about because of this rope that keeps them moving together. These are two examples of constrained motion. And how to deal with this when the motion becomes quite complicated or number of masses increase or number of constraints increase is going to be the topic of discussion in today's lecture. So let us start with our first example, that is a mass or a bead moving on a straight wire. As I said, in x direction, let's say. Through this example, I would like to introduce terminologies that are going to be in use when we talk about constrained motion. So if I apply a force on this, what does the wire do? The wire applies a normal reaction on this body. Why does the wire apply a normal reaction on this body? Because it doesn't want it to move anywhere except along the wire. So it is this normal reaction N that is really restricting the motion of the particle along the wire. This is called the force of constraint. To recap it, I'll again say that the effect of this wire on this body, I'm making it slightly bigger now, is just to produce a force N or a force of constraint. If you look at this body, I have replaced the wire by this force of constraint. This is known as the free body diagram of a particle or a body under motion. So what do we mean by free body diagram? By that I mean I'll make the body by itself, nothing else, and represent all the forces applied externally or applied by the constraints on it, and that I'll call free body diagram. Let us see how do I write the equations of motion for this body. Since the normal force is going to be perpendicular to the wire, so N is going to have only two components in y direction and in z direction, and x is always going to be 0. The force F that I have applied, or I should write a vector here, is going to have all three components Fx, Fy and Fz. With these components of the forces, the equations of motion of this particle are going to be mx double dot equals Fx because Nx is 0, my double dot equals Fy plus Ny, and mz double dot equals Fz plus Nz. These are three equations of motion that I get from F equals ma. Let us see how many number of variables there are. There are x, y, z, n, y and nz. 5 variables. On the other hand, I have only 3 equations. So I have 3 equations and 5 variables. Obviously, with this I cannot solve the problem. Where do I get the 2 other equations from? And this is where I start thinking the 2 of these variables, n, y and nz, came because I imposed a constraint. So the equations should also come from the constraints themselves, and that is precisely where they come from. The equations of constraints are that y is equal to 0 and z is also equal to 0, and this implies y dot or y double dot both are 0, and so is z dot and z double dot. So I have 2 more equations, total 5 equations and 5 unknowns, and I can solve the problem. Let us now look at the second example of constrained motion that I considered earlier, and that was the Atwood's machine, in which 2 masses are tied on a string that is passing over a pulley that is massless and frictionless, and so is the string. So let us write again. This is mass m1, this is mass m2, rope or the string is massless for simplicity, and pulley is massless as well as frictionless. You may have solved this problem time and again in your previous courses, but what I want to focus on here is how to really deal with it from the constrained motion point of view. And therefore, first thing I am going to do is see what is causing the constraint. The constraint is caused by this rope that forces the 2 masses to move together. What is the force of constraint here? The force of constraint that really makes the masses to move together is nothing but the tension in the rope. So tension in the rope is the one that keeps these masses together. Next, if I were to make the free body diagram, for the 2 masses, let me remind you again what a free body diagram is. A free body diagram is where I replace the agency causing the constraint by the force of constraint that it applies. So if I were to make the free body diagram for mass m1, it will be something like this, that there is a force pulling it down, m1g, the gravitational force, and there is a tension T, which is the force of constraint pulling it up, and that is a free body diagram for mass m1. Similarly, I can make free body diagram for mass m2, that will also be similar, m2g pulling the body down and tension T pulling it up. You may ask me at this point, why did I keep the tension the same? The tension remains the same because the pulley is massless, frictionless, and the rope is also massless, and therefore it doesn't require any force to move them. And that is what I said earlier. I had taken massless rope, massless pulley and frictionless pulley to keep things simple, because I want to focus on the constraint part of it. Now let us write the equations of motion. If you recall from the previous slide, the m1g and m2g are acting down and T is acting up on both the bodies. So equation of motion is going to be m1 a1 in y direction is equal to T, which is pulling it up, minus m1g. m2 a2 in y direction is equal to T minus m2g. You may ask, I am writing a1 y, a2 y, which way is my y, and things like those. So let us be more precise. Let me measure my distances from the ground and be more precise, because that will also help me later to write my constraint equation. Let this be the ground. Let the distance of mass m1 be y1 from here. Let the distance of mass m2 be y2 from here. Let the center of this fixed pulley be at height h from the ground. And now I can write, this is tension T pulling it up, m1g pulling it down, tension T pulling it up, m2g pulling it down, and therefore I can write m1 y1 double dot is equal to T minus m1g. Notice that all the directions and everything is correct. I must take care of that because we are dealing with vector quantities, although I am writing this in one dimension. Similarly, m2 y2 double dot is going to be equal to T minus m2g. I have gotten my two equations of motion, but again the number of variables are y1, y2, t, 3. So one equation that is missing must be provided by the constraint itself, and that is where this picture comes in handy. Recall again, the constraint that the two masses move together is provided by the fact that the rope is of fixed length. And I can express this mathematically as this part, which is h minus y1, plus this part, which is h minus y2, plus this part is of constant length. Since this part is always of constant length, I can write my constraint equation as h minus y1 plus h minus y2 is equal to a constant, or shuffling terms around, I can write this as y1 plus y2 is equal to a constant. This is my third equation. To bring it to usable form, in the equations of motion I differentiate it and then get y1 dot plus y2 dot equals 0, and also y1 double dot plus y2 double dot is equal to 0. So let us write the equations once more. Again, I am solving this problem of two masses attached to a string which is passing over a fixed pulley, I have m1 y1 double dot equals T minus m1g, m2 y2 double dot equals T minus m2g, and y1 double dot plus y2 double dot equals 0. I have 3 equations and 3 unknowns, and I can solve my problem. Notice this constraint equation just tells you that when one particle is moving up, the other one is going down. When one particle is accelerating up, the other part is accelerating down. Let us now solve these equations. Let us eliminate T first. So for that I subtract equation 2 from equation 1. In doing so, I get m1 y1 double dot minus m2 y2 double dot is equal to m1 minus m1g plus m2g. Since I know that y1 double dot plus y2 double dot is equal to 0, this implies y1 double dot equals minus y2 double dot. If I substitute, I get m1 plus m2 y1 double dot equals m2 minus m1 g, or y1 double dot equals m2 minus m1 over m2 plus m1 g. A result you already know. If m2 is heavier than m1, then y1 double dot is up, and that is precisely what I am getting. You see, I did not make any assumption about m1 or m2 being lighter or heavier and things like those. The results automatically popped up. Through these 2 examples, what I have tried to demonstrate to you, that constraints in a particle's or a body's motion can be caused either by external agencies, as we did in the case of a particle moving on a wire. The constraint was caused by this wire, or by other body itself. That is, in this case, this mass m1 and m2, when they were connected by this rope, this was providing the tension, but the presence of one mass restricted the motion of the other mass. And also, when we solved these 2 simple problems that you already knew the answers of, we also tried to develop stepwise strategies to solve motions of different bodies when they are moving under constraints. Let us try to write them. So first step in solving a problem is going to be identify the constraints and forces of constraints. Once I have identified the constraints and forces of constraint, the second step is make free body diagram of all bodies, and these bodies, which are treated separately, are also called subsystems of the system. Let me remind you what a free body diagram is. When I make free body diagram for a body, I make that body freely and consider all the forces that are being applied from outside and the constraint forces on it. There may be more than one constraint force, and that is my free body diagram. The third step is going to be then write the equation of motion for each subsystem. At this stage, you will see that the number of variables in the problem is more than the number of equations that you have written, and therefore there are some missing equations, and these equations are going to be provided when you write the equations of constraint. Constraints, there may be more than one. Still, if the equations don't match, either you have missed something or you have misformulated the problem. Go back and do it all over again. And once the equations and number of variables match, the last step is solve the problem.